Okay, practicing equilibrium constants a little more. The flavor of fruits and berries is because of esters. We've met those. And ethyl propanoate, this, is responsible for the flavor of pineapple. It's produced by a reaction that goes blah, blah, blah. And they give us a K, and they tell us that the K is 2.2. So anytime you mix these chemical species, the ratio of products over reactants, it might not be 2.2 initially, but it's going to work its way towards 2.2. If you put these things in a bowl and then go out for lunch, it should be 2.2 when you come back. Unless this is a really slow reaction, you might have to go home for the weekend if it's kind of a gradual change. But always these concentrations will change until the ratio becomes 2.2. Speaking of which, what is the ratio for this? What's our K? Well, we've kind of trained ourselves to see liquids and start scratching them out, but look at this. Liquid, 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 liquid. When the entire mixture is liquids, you count them all. And so for this thing, we're going to count every single one of these species. We're going to count the ethyl propanoate, which I'm not real excited about writing out, but oh well. COOC2H5. Water. You even count the water. And then we have ethanol. And C2H, that's a propanoic acid. Okay, so there's all our Ks. And now they're having us do a number crunch with this because they've told us the concentration of the ethyl propanoate is 2. It isn't really necessary to stick with square brackets, but I always seem to do it, and so do a lot of other people. So, okay. Concentration of water, I do not know. We'll call it W for water. If you want to go with X, fine. Concentration of ethanol, 5. And concentration of the propanoic acid, they say is 0.1. Okay, so we have all those concentrations, and they tell us if we're at equilibrium, the K will be 2.2. So now we must solve this. That's 2W over 5 times 0.1 is 0.5 equals 2.2. I want to isolate the W. Right now it's divided by 0.5, so if you multiply both sides by 0.5, you get 2W equals 1.1, and then divide both sides by 2, and you get W should be 0.55 moles per liter. That's the concentration of water in that equilibrium. And why did we include water in the equilibrium? Because the whole thing was liquids. You ignore liquids unless it's all liquids, in which case you give in to the liquids and count them all. Okay, and I believe all the rest of these are calculations using a K. So they give us concentrations here. Calculate the value of the equilibrium constant. Well, we've got a reaction here, so we can say the equilibrium law for this thing is ammonia squared, because of the coefficient there, over nitrogen to the power of 1. I'm not going to write that. And hydrogen to the power of 3. And they tell us they got this system to equilibrium and found the ammonia was 1.23. I'm going to switch to round brackets just to prove that you can. So our K is 1.23 over nitrogen 0.885 and hydrogen is 0.665, and that's to the third power. Please note, when you're doing a setup like this, you can't just use any concentrations that someone happened to measure. You have to know that you're at equilibrium. Here they said the equilibrium concentrations for the reaction. That means that these are okay to use. But if someone says, I put the following concentrations in a bowl, blah, 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 that's probably not an equilibrium mixture, and it is not safe to put it into your K. because the system is not at equilibrium yet. So if we calculate this thing, 1.23 squared divided by 0.885, also divided by 0.665 to the third, and I get that the K for this is 5.81. All these had 3 significant digits, so giving the K to 3 digits is probably okay. Okay, sulfur dioxide. Remember to check if there's anything that we're ignoring in our K here. Gas, gas, and gas means that we keep all this stuff. The equilibrium constant for this is, I haven't even read the problem yet. I just assume we're going to need a K because we're in that part of the unit. Sulfur trioxide. Oh, I went back to square brackets just kind of automatically. Remember to square it. And then we have sulfur dioxide. Now that I've started using square brackets, I feel obligated to stick with them. And oxygen to the power of 1. Okay, at equilibrium, they have the spinning moles of SO3 and the sulfur dioxide and the oxygen, and they want the equilibrium constant. So, same as in the last problem. Now look out. If you're thinking of writing a 3 up top, you missed something. These are moles. The K requires concentrations which are in moles per liter, and that means these moles are no good, and these moles are no good, and these grams are definitely no good. So we get to put our K on the back burner and do some mole calculations before we can go on. I'll do this kind of fast because I think you're probably experts by now. Concentration is number of moles divided by volume. For the SO3, the concentration is 3 moles divided by 0.5 liters is 6 moles per liter. For sulfur dioxide, it's 2.25 moles divided by, they're in the same container, so still, again, 0.5 liters. That'll be 4.5 moles per liter. And for the oxygen, concentration is, well, the volume is 0.5 liters. The number of moles is mass divided by molar mass. So 100 divided by 32, 3.125 moles. That's a lot of steps happening all at once, but I trust you've done a few molar masses by now. And if that did lock you up, get a hold of the instructor and they can walk you through it. 6.25 should be the concentration for the oxygen there. Moles per liter. Okay, now we're good to go to our K, now that we have concentrations. The sulfur trioxide is 6 squared. The sulfur dioxide is 4.5. Also squared. The oxygen is 6.25 first power. So if we calculate that, 6 squared is 36, divided by 4.5 squared is 20.25, I believe, and also divided by 6 1/4, 0.284 is what I get for that one. Okay, getting away from real chemicals for a minute. The equilibrium constant for this is 10, so I'll set this out quickly because we're going to need it. For the forward reaction, all right, the first one that they wrote is what we call the forward reaction. And then they write the same thing backwards, and this is called the reverse reaction. So remember I was saying sometimes we'll subscript our K's to help us keep track. I'm going to write 2 K's here, and I'm going to call one of them K forward, and I'm going to call the other one K reverse. And those subscripts will make sure that I don't get mixed up on which one's which, hopefully. For the forward reaction, the K is products over reactants, so it's C times D over A times B. Concentrations of the products, and they're both first powers, over concentrations of the reactants, and they told us that comes out to 10. For the reverse reaction, Now the products are A and B. Oops, sorry. Not together, though. I don't know where I got that idea. Concentration of A times concentration of B over the concentrations of C and D. And they ask what that equilibrium constant is. Well, you notice how this K and this K are reciprocals of each other? They're the same fraction, only one's upside down. That's true for the concentrations. It's also true for the number out here. If this number is 10, or you might want to think of it as 10 over 1, then the reverse reaction is going to have a K of, flip this over, 1/10. If this thing had a K of 75, you could think of that as 75 over 1. This thing would be 1 over 75. If this thing was 0.668, for this one you could write 1 over 0.668. And probably you'd do that on the calculator, and either of these you'd probably do in the calculator. 1 divided by 75, 1 divided by 0.668, and that would give you a nicer version for the equilibrium constant. So the takeaway from this, if you know one reaction's K, if you reverse the reaction, you flip the K over, you do its reciprocal. It doesn't go negative or anything like that, it just gets reciprocated. Okay, equilibrium constant for this reaction. These are all gases, so we're not going to ignore any of them. I'll throw up K right now just because pretty likely we're going to need it. Hydrogen fluoride. It's not hydrofluoric acid because it's dry, it's in gas form. Although if it touched any water, it would turn into hydrofluoric acid. Remember to square that. And then we have hydrogen and fluorine. That's a lot of dangerous chemicals all in one place. Okay, has the value of 2,100 at a particular temperature. When the system is analyzed at equilibrium, the concentrations of hydrogen and fluorine are both found to be bleh. What is the concentration of HF? Okay, we should be able to do this. HF, we don't know. Hydrogen, they say, is 0.0021. And fluorine is also 0.0021. And that has to come out to 2,100, they say, is our equilibrium constant. And now this is a solve for X. I'm going to do a shortcut because there's a shortcut here that comes up kind of often, and I want to make sure you see it. You noticed, I assume, that these two are exactly the same number, and that means instead of writing 0.0021 twice, I can write 0.0021 squared and then lose the second one. Would you agree, I hope, that that's the same thing? The reason that's useful, what have I done? Tried to make it better and I made it so much worse. There we go. Okay, the reason that's useful is if both of these are squared, it'd be nice to get rid of those squares, and there's actually a way we can do that very simply. We can square root both sides of this. If we square root the left side and square root the right side, on the left side, this root is going to strip off both of those squares. The squares and the square root will cancel each other. And so on the left side, all that will remain is x over 0.0021. None of them are squared anymore. That's nice. Sadly, on the right side, we have a different number now. We have to do the square root of 2100. And I get 45.83 for that. So, improvement on the left side, a bit of a step back on the right, but oh well. How do we solve this for x? We have x divided by 0.0021. The opposite of dividing by that would be multiplying by 0.0021. So if we multiply both sides by 0.0021, we get 45.83 times 0.0021, and from that I get 0.096 moles per liter. The K and this concentration both had two significant digits, so I cut off the X at two significant digits also. That's probably okay. And declarative knowledge question. What can you do to change a K? Almost nothing, but K changes if you vary the temperature of your system. There are some reactions that don't happen at all at one temperature, but the K rises rapidly if you change the temperature. So heating or cooling a system will change its K. If you cook, you know that. You know that if at room temperature, eggs cook very, very slowly. In fact, they basically don't. But if you put them on a hot pan, they start to cook very quickly. That's because there are equilibria in the reactions in an egg that just don't go worth a darn at room temperature, but they start to occur very quickly if you apply a little more heat. That's another way of thinking about endothermic reactions, is the reactions where the K changes a great deal as you change the temperature. So change the temperature. There is no fixed rule that I am aware of for what changing the temperature will do. Some reactions the K goes up with heat, some reactions the K goes up with cold, but for sure we know that changing the temperature will change the K somehow. Okay, a bit of a marathon here. Equilibrium conditions for a hydrogen iodine system. This is just some rapid fire calculations using Ks. They give us a reaction, and so we can write an equilibrium law for it, which would be, these are all gases, so we're going to keep them all. The product is hydrogen iodide, and it should be squared. And then we have hydrogen and iodine. They don't tell us what that number is, sadly, but we can figure it out because they've given us this equilibrium where we know everything else. So we can use this to pick off our K. The K will be, let's see, hydrogen iodide is 1 squared. And I'm switching to round brackets because they're easier to write now. Hydrogen is 0.4. And iodine is 0.5. So if we calculate that, we get 1 over 0.0, or sorry, 0.2, my bad. And that equals 5. So just from this, we know that the K is 5. That means it's 5 all the time. Anytime you combine hydrogen iodine and hydrogen iodide, the reaction is going to go so that it tries to reach an equilibrium. It tries to reach a ratio of 5, and then it'll settle down. So we can use this 5 for all the remaining problems. For all those, we know that product over reactants has to come out to 5, and we can use that to solve other stuff. So in B, we already have our equilibrium constants. We can use that again. Our HI is 8.5. So 8.5 squared over hydrogen 0.16. And iodine, I don't know. I'll call it B because this is question B. That has to come out to 5. Can we solve that? Probably. Let's see. 8.5 squared is 72.25 over 0.16b. Trying to make my b's not look like 6's. Equals 5. Multiply both sides by the denominator. 72.25 equals 0.80b, or 0.8b, and divide by 0.8. 90.31. That has to be 90.31 moles per liter. That's awful high. I guess it's making up for the hydrogen, which is awfully low. Just 'cause this number is so high and it's worrying me a little bit, I'll show you how we can check one of these if you're having doubts. When you think you've got a solution, we know that these numbers have to obey the original K, right? So we can take this HI and this iodine and this hydrogen, plug them back into here, and we should get 5. If we do that, here's my check for B. I'm going to do HI 8.5 squared over hydrogen's 0.16 and iodine's 90.31, we hope. 8.5 squared divided by 0.16, also divided by 90.31. Yeah, I get 5.000 and then some small change that doesn't matter. So yes, this number is good. We got our K of 5. That means these are consistent. All right. How about C? Now it's the hydrogen we don't know, so we can start with our K again. It's product, so 3.75 for the hydrogen iodide squared over hydrogen, which I do not know. I'll call it C because we're doing question C now. And iodine is 0.333. And we know that has to come out to 5 because the constant's always 5. 3.75 squared is 14.0625. Downstairs we get 0.333C equals 5. Multiply both sides by the denominator. 0.333C times 5 makes, oh sorry, our left side is still 14.0625. And on the right side we get 0.333C times 5, which is 1.665C. And then we divide by 1.665 on both sides. So 14.0625 divided by 1.665. And we get C equals 8.45 moles per liter. Good. Clear out some room. Okay, D. Now they don't give us the iodine. No big deal. HI is 22.4. Remember to square it. Hydrogen is 356. 3.56, I should say. Iodine is, I'll call it D because we're on question D. And the equilibrium constant is 5. I erased that, but you probably remember, and I do too. Okay, so solving this, 22.4 squared is 501.76. Downstairs we get 3.56D equals 5. Multiply both sides by the denominator, 3.56D, and we get 501.76 equals 17.8D. And divide both sides by 17.8. And I get 21.2, or I'm sorry, 28.2. 28.2 moles per liter for the iodine. Now, this last one, I think there's some kind of print error here. This times looks to me like they meant to write times 10 to the minus something, give us a very low concentration to see if we can handle it. But we don't have the powers, so there's no way of knowing what they meant those numbers to be. So just to get us some more practice, we'll make the best of this. Let's just pretend those aren't even there, and we'll just say that the hydrogen and the iodine are 4 and 9. And at least that way we can do this problem. Probably the answer is supposed to be times 10 to the minus whatever, but since those numbers are missing, Oh well, we'll just carry on as best we can. So our K is hydrogen iodide, which I do not know. All right, E, because we're on question E, and remember to square it. Hydrogen is 4, iodine is 9, and all that has to come out to 5 because that's our equilibrium constant. Constant means it doesn't change, it's the same all the time. So we get E squared over 4 times 9 is 36 equals 5. Multiply both sides by 36 and we get E squared equals 180. And then we have to square root that. I suppose we could have done that here, but then we would have rooted 36 and 5, and that's a bit of a nuisance. It's a little easier if we do it at this stage. Square root the left side, square root the right side. On the left, the square root and the square kill each other, leaving us with just E. And on the right side, we get the square root of 180, which a calculator can do for us. It's 13.4. 13.4 moles per liter. Now, I have not checked the key for this. If you find that this answer is something else, it'll be because they had powers here. It was times 10 to the something. And without knowing those, we're not going to get the right solution for this. At some point, I'll have to go back and fix this problem. So those either put in the powers or clean up the x's. But for now, this is what we got.